In this demonstration, I'll talk about the deep learning tools that are available in ArcGIS Pro. The scenario is focused on detecting solar panels and pools within property parcels. Doing this process manually could be a daunting task, and here's where deep learning comes into play. I go through the entire workflow in Pro and explain the tools and parameters along the way. First step is I need to capture training samples. While you can use regular editing tools for the task, we've added a labeling tool specifically designed for deep learning workflows. I can dive right in and start capturing training samples, but this being an object classification workflow, instead of capturing training samples using the attribute pane, I just need to attribute the parcels appropriately. We can update the parcels to specify if it contains pools, panels, or a house with both. Let's label a couple parcels. In the interest of time, I've captured or labeled the training data I need. Now we can directly move to the next step, which is exporting training samples. The deep learning toolset within the image analyst toolbox gives you access to all deep learning tools. Step 1, export training data. This tool essentially creates the image chips and exports relevant metadata which will be used to train your deep learning model. You specify the input raster, the output folder where the chips are written to, the input feature class or thematic raster, which essentially is the training samples or labels. The input mask polygon is typically used when you have sporadic training samples. Tile size is the size of the output chip size which will be used to train the deep learning model. Larger chip sizes will be faster to process, however, require more GPU memory. Stride is the amount of overlap when creating chips. Best practice here is half the tile size. This increases the number of samples and this also accounts for edge artifacts within each chip. Rotation angle provides additional augmentation of your chips. Reference system, you can work in map space, which is typical, or if you have access to the transforms, you can work in image space. Benefits of this, you can get rid of distortions that are typically caused by autorectification. The output no feature tiles option is useful when you want to provide additional chips for training where you're essentially defining what is not there. There are several metadata formats that we support, each for different types of problem sets. The output of this tool is a bunch of training chips and metadata. And here are some of the chips. Next step is training your deep learning model. I'll quickly go over some of the parameters. First, you provide the input folder that contains the training chips. Max epoch defines the max number of times a data set would go back and forth through the neural network, essentially number of cycles of training the data. If you have a lot of training samples, you can keep this number low. Model type, we have a range of models, each one used to solve a specific problem. Batch size is typically a power of 2. Increasing this batch size is directly proportionate to the GPU resources you have. Increasing the batch size on a low GPU will result in out-of-memory errors. Each model has its own set of arguments. We use intelligent defaults, so you don't really need to tweak the advanced parameters, but it's available for advanced users. The learning rate is the most important hyperparameter. It's the step size by how much the weights will be increased or updated during training. Going too low and the model will take forever to train. It'll improve very slowly with the model not really showing much difference with each epoch. Going too high, the model may not learn well. It's analogous to someone being too quick to come to conclusions. This pre-trained model parameter lets you incrementally train and improve a model. Typically, you train in multiple phases using a lower learning rate each time. You can train an existing model with more data or better data to improve it further. You can also use this to adapt a previously trained model on a different geography, different imagery, or in some cases, different classes. The validation parameter lets you specify how many training samples should be set aside for accuracy assessment. The freeze model parameter specifies whether to freeze the backbone layers in the pre-trained model so that the weights and biases remain as originally designed. Turning this off will result in weights and biases being altered to fit your training data. This takes longer and you might get better results. The output is a trained model. It's a deep learning package that contains an Esri model definition file and the trained model. This is used for the next step. Lastly, running inferencing. This could be object detection, pixel classification, or object classification, all of which for we have relevant tools. The inferencing has to be run over an area in Redlands, in this case, with 1,400 parcels that need to be updated. The input data, the output feature class, training model are the key parameters for inferencing. Here are the results. Stepping through the results, here's a parcel that has a pool, another one with solar panels. So that was a deep dive of the deep learning tools that are available in ArcGIS Pro.